the name of Almighty God, I'm Master Sankosh, and today I want to talk about nuclear fusion. High energy neutrons are the main product of deuterium-tritium nuclear fusion reaction in operation. These neutrons will penetrate reactor materials interacting with the atomic nuclei. These interactions produce atomic recoils, which create collision cascades with the material, leading to the production of dislocations, voids, and other microstructural defects. These defects cause degradation of the reactor material's mechanical and thermal properties. Nanocrystalline material have been considered for use in fusion applications due to their high grain boundary density, which may act as a sink for radiation-induced effects. These materials are characterized by their small grain size, less than 100 nanometer, and experimentally a lower irradiation defect density has been observed for non-crystalline materials when compared to coarse grain materials irradiated to the same dose. Experimental techniques such as high-pressure torsion, accumulative roll bonding, and equal channel angular pressing have been extensively used to produce non-crystalline materials through severe plastic deformation. Traditionally, molecular dynamics or MD studies on the non-crystalline material have used Voronoi tessellation with randomly placed grain seeds to generate non-grained simulation cells. Recently, studies have been carried out to the creation of non-crystalline materials in MD through SPD. Tolkachev and his colleagues induced grain refinement in iron by applying a high shear stress up to gamma is equal to 10 to initially pristine simulation cells. Non-grain formation was directly observed, and grains were found to be stable at constant temperatures of 300 Kelvin, 500 Kelvin, and 800 Kelvin for 1 nanosecond. Irradiation-induced annealing processes have been observed in materials both experimentally and through AMD simulations. Song and his colleagues irradiated non-crystalline and coarse-grained UFR-97 with self-ions, and the irradiation-induced annealing process was revealed through X-ray diffraction measurements, which showed grain coarsening and a reduction of dislocation density with increasing radiation dose. Ma and his colleagues used MD simulations to study radiation damage in non-crystalline tungsten by utilizing the creation relaxation algorithm. Similarly to the experimental findings, a grain coursing occurred with increasing dose. Levo and his colleagues also observed radiation-induced grain growth in non-crystalline nickel subjected to collision cascade simulations. Tolkachev and his colleagues reported a grain coursing with radiation in non-crystalline iron. The combined atomistic an experimental study also confirmed grain coursing in self-ion irradiated non-crystalline ion disks, and the MD data suggested a linear grain growth, which was consistent with experimental values. Every grain within a material will have inherent elastic energy due to the elastic strain field associated with grain boundaries and crystal defects. It is expected that the radiation-induced annealing process reported both in experiments and MD simulations will reduce the elastic energy as grain grows and annealing occurs. The potential energy will be a sum of defect formation energy, grain boundary energy, and elastic energy. As such, they are tracking the excess potential energy as a function of radiation is a useful method of measuring the integrated effects of grain growth and defect reduction for initially non-crystalline MD simulation cells. Reduced activation, ferrite, and martensitic RAF seals such as Eurofer 97 and T91 are promising candidate materials for future nuclear fusion reactors. Previous studies have explored their radiation resistance, and Garner and his colleagues reported that raft missiles with body-centered cubic structure were more resistant to radiation-induced swelling than authentic seals. Raft missiles or reduced activation ferrite martensite seals are iron-based alloys, and in this work we use iron or Fe as element as a prototype material to gain mechanistic insight into its evolution under irradiation. They established a method for simulating radiation damage using DMD simulations is through collision cascades. This method selects random atoms in a simulation cell and assigns velocity in a random direction corresponding to an expected primary knock-on atom energy. In this work, non-crystalline iron cells created through Voronoi tessellation and through the shearing method reported by Tolkachov and his colleague are considered. These cells are subjected to radiation through collision cascade simulations and the evolution of excess potential energy, which the cells extract as a function of those. First, excess potential energy is calculated for all cells are compared. The excess potential energy is calculated for each individual grain for different types of starting microstructures. This gives insight into how grains evolve during radiation. Finally, the implication of these results is discussed before drawing conclusions. Now, I want to talk about the methods. The first method is simulation steps. Lamps was used for all Emily simulations in this work. Two distinct methods were employed to generate non-crystalline iron cells: Voronoi tessellation and high shear strain method proposed by Tolkachov and his colleague, hereby denoted as the shear cells. In the case of Voronoi cells, two different grain numbers were seeded for comparison, one with 5 grains per cell. The AC is equal to 16.6 nanometer, and the other with 20 grains per cell. The AC is equal to 5.2 nanometer. The diameters are calculated using the spherical grain approximation. 5 independent cells are created for each initial condition, and the results and error below are calculated with respect to 5 simulations for each type of microstructure. For comparison, 5 additional initially pristine iron cells were also irradiated through collision cascades. All cells contain 1,024,000 atoms, which corresponds to 80 multiplied by 80 multiplied by 80 units. Cells of BCC iron. The cell relaxation method reported by Emma and his colleagues was followed for all distinct simulation cells. An extra step was added to the shear cells in that they were initially thermalized to 300 Kelvin and sheared up to gamma is equal to 10. By utilizing the method in reference 26, the cells achieved stress-free conditions and were brought down to the temperature of 0 Kelvin before collision cascade simulations. The data set considered here was also used in Tolkachov and his colleagues. Previously, Tolkachov and his colleagues determined that the Voronoi cells grain volume correlated well to the equation of their friends and his colleagues, whilst the grain volume distribution of the shear cells was fit to zipped Mandelbrot model. The potential used in this study, the Mandelbrot and his colleagues, and the iron 2 potential, this belongs to the Auckland and Mandelbrot family of iron potential, which have been used extensively for the study of radiation damage effects in iron and iron alloys. Indeed, Malherbe and his colleagues commented that the Mandela type potentials are the best choice for studying radiation effects on iron when compared to density function theory. Collagen cascade simulations were employed to replicate neutron damage in the non-crystalline urine. The method in the Tolkachov and his colleagues was followed, which is based on the collagen cascade method developed by Bolinier and his colleagues, the stopping a range of ions in matter. Code was used to determine the recoil energies of primary knock-on pKa atoms in ions. These recoil energies were sampled from for each collision cascade simulation to ensure a target dose was obtained in each step. Appendix A of Tolkachov and his colleagues shows the recoil energy distribution that was sampled in this work. It is dominated by lower energy recoils, which is between 30 to 200 electron volt, with a much lower probability of selecting higher energy recoils, which is between 200 electron volt to 220 kilo electron volt. The exclusion radius of each pKa is also calculated to ensure there is no overlap between cascades. Each distinct simulation cell was irradiated to 5 dPa with a single instance of each cell type being irradiated to 10 dPa through collision cascade simulations. Each primary knock-on atom energy was converted to damage energy through the Linhart model, which informed the Narget-Robinson-Torrens model used to determine the number of atomic displacements generated by any given cascade. This method is used to measure the applied dPa between steps. High dose rates, which is the derivative of phi beta based on the time, is almost equal to 1 dPa per 50 nanoseconds, are present in the simulation due to the time limitations of MD simulations, effectively meaning that the MD simulations will only show fast processes such as stage 1 and stage 2 recovery, but the slow processes with high thermal barriers will be missed. Hence, the cascade simulations are propagated in an athermal regime. This has previously produced a credible representation of irradiated material and is also suitable for comparison with room temperature and experimental data on iron. Computational analysis. The OV2 code was also used for the analysis. Polyhedral template matching, or PTM, was used to determine local atomic orientations, which were fed into the grain segmentation modifier to identify which atoms were part of which grains. To calculate the mean excess potential energy per grain, the excess potential energy of each atom in the grain is calculated. And mean overall, the atom is taken. The excess potential energy of the entire simulation cell is also calculated using Laplace. Excess is taken to mean the potential energy in electron volt per atom of a given grain or cell subtracted from the potential energy of a a pristine defect-free iron cell at the room temperature with attraction-free boundary conditions. Results sections. Figure 1 shows the mean grain number as a function of dose for all initially non-crystalline iron cell, averaged over the 5 distinct simulations of each type of starting microstructure. A clear radiation-induced annealing process is shown whereby the grains in all initially non-crystalline cells grow and become single crystalline after almost 2 dPa. In Tolkachov and his colleagues in the reference 28, which uses the same dataset, the radiation-induced grain growth was found to be consistent with random grain growth. Furthermore, the study confirmed radiation-induced grain growth experimentally in self-iron irradiated non-crystalline iron. Similar behavior has previously been observed using molecular dynamics simulations. Ma and his colleagues observed radiation-induced grain growth in non-crystalline tungsten, whilst Levo and his colleagues show a grain growth in non-crystalline nickel. with all cells becoming single crystal with increased dose. Experimentally, irradiation-induced annealing has also been observed in numerous studies. Excess potential energy versus dose is plotted in Figure 2. The initially pristine cells are also added here for comparison. Figure 2a shows the overall excess potential energy in electron volt per atom for each starting configuration, averaged over 5 independent simulations. As expected at 0.001 dPa, the shear cells have highest excess energy due to the large number of grain boundaries and defects present within the cell. The DC is equal to 5.2 nanometer cells have the next highest, followed by the DC is equal to 16.6 nanometer cells, which is again expected as having smaller grains and grain boundaries overrates the excess potential energy. All initially non-crystalline cells follow a similar trend. Excess potential energy increases before decreasing and seemingly plateauing at similar values above for dPa. This is more evident in Figure 2b, which shows a zoomed-in view of excess potential energy between 2 and 5 dPa. It is noticeable, particularly after 4.5 dPa, the excess potential energy in the initially non-crystalline cells seemingly converges at similar values of 0.022 till 0.023 electron volt per atom, with much overlap in the standard deviations. This seems to suggest that irrespective of the initial starting configuration, all initially non-crystalline cells will converge at similar values of excess potential energy at high dose. In Figure 2a, the initially pristine cells don't follow the trend of the initial non-crystalline cells. The excess potential energy only increase with the dose. Interestingly, the excess potential energy of the pristine cells nearly matches that of the initial non-crystalline cells, being almost equal to 0.021 electron volt per atom at 5 dPa. We also note that the excess potential energy in the pristine cells is seemingly still increasing at 5 dPa, and hypothesis that it will continue to increase until it reaches the range of the initial non-crystalline cells. You see, we have in x-axis irradiation dose based on dPa, and in the y-axis we have excess potential energy, electron volt per atom. And you see that the green line, which is showing the shield, is much more, and pristine in the purple is less, but the orange and blue are in the middle sections of electron volt per atom. Also, we have irradiation dose in the x-axis and excess potential energy electron volt per atom in the y-axis. Figure 2 shows excess potential energy versus dose for initial non-crystalline and pristine cells in electron volt per atom. A plotted between 10 to the power of minus 3 dPa and 5 dPa. B plotted between 2 dPa and 5 dPa. So the difference between the A and B is that you see radiation dose is in x-axis between 2 and 5, but here between 10 to the power of minus 3 until 1. Figure 3 illustrates damage against excess potential energy for a single instance of each simulation type between 2 and 10 dPa. To test this hypothesis, a single instance of each simulation type was run to damage of 10 dPa, and the excess potential energy for these simulations between 2 and 10 dPa is shown in Figure 3. It is noticeable that both the shear and the DC is equal to 5.2 nanometer cells have plateaued beyond 2 dPa at almost 0.022 electron volts per atom. However, the Bernstein cells is at 0.020 electron volt per atom at 2 dPa and rises to 0.022 electron volt per atom by 9.5 dPa, seemingly plateauing after this dose. This seems to confirm the hypothesis above, whereby all simulation cell types will converge to similar excess potential energy at high dose, irrespective of their initial starting configuration. Figure 3 dose, however, show that the excess potential energy for the DC is equal to 16.60 nanometer cell, reduced to almost 0.020 electron volt per atom after 6 CPa and plateaued here. It is not immediately obvious why this occurs. However, this variation is on the same scale as simulation to simulation fluctuations. To evaluate how the excess potential energy evolves for individual grains, histogram of excess energy versus the grain size for all simulations are presented in Figure 4. Figure 4a, the data for the DC is equal to 16.6 nanometer cells is run initially at 0 dPa. All grains have similar excess energy and size. By 0.5 dPa, there is a noticeable grain growth, with some grains getting larger. Note here that some grains get smaller, corresponding to a higher excess energy. By 1 dPa, there are more larger grains of lower energy and some smaller grains of higher energy. Figure 4b shows the same data for the DC is equal to 5.2 nanometer cells. Again, a similar grain growth process is observed and a direct correlation between grain size and excess potential is visible. At 1 dPa, there are numerous larger grains with lower energy and smaller grains with high energy. As with the DC is equal to 16.6 nanometer cells. The data for the sheared cells in Figure 4c follows a different evolution. As in Figure 1, there are many more grains in the sheared cells, and this is reflected in the 0 dPa figure. By 0.5 dPa, the number of large grains has increased, with some smaller grain of higher energy and a noticeable decrease in grain number as per Figure 1. Note that the similarity in histogram between all cell types at 1 dPa, whilst the number of grains is different, there is a noticeable trend in evolution, notwithstanding the starting microstructure. Appendix R depicts the histogram data for all cells at 5 dPa, and this shows that the excess potential energy per grain does plateau at EF. At this dose, all cells are single crystalline, so the grain diameter becomes arbitrary. So thank you so much for watching my tutorial video until the end. Uh, Also, you can download the proper simulation from my github.com/masterscape2 is the 4th day of June 2026. Time is 8:19 p.m.